Hello students, so today module 18 we are going to do calculation with weak acids. Please go page 17 of your notes. So this is the last slide from module 17. We established, based on an ice table for a weak acid, an expression for Ka, which is x squared divided by the nominal concentration minus x being the change that is being established as the equilibrium is reached. And we said that given H3O plus and Ca, we could find Ka. Given Ka, H3O plus, we could find the nominal concentration. Given Ka and the nominal concentration, we could find the concentration of H3O plus or the pH. So let's do examples of that now. So calculating the Ka for a weak acid. Question 9. The pH of a 0.1 molar lactic acid is 2.06. What is the Ka for lactic acid? So we have this equilibrium that is being established. Initially, we have 0.1 molar lactic acid and no H3O plus, no lactate ion. There's a change whereby a little bit of lactic acid, X, is converted into H3O plus and lactate ion. So at equilibrium, we have 0.1 molar minus X concentration of lactic acid, and we have plus X concentration of H3O plus X of concentration of lactate ion. We can write the equilibrium constant for lactic acid. It's the concentration of H3O plus at equilibrium times the concentration of lactate ion at equilibrium divided by 0.1 minus H3O plus at equilibrium. The concentration of H3O plus is given from the pH. It's the antilog of pH, so 10 to the negative 2.06 or 8.7 10 to the negative 3 molar. Now recognize that the concentration of H3O plus equals the concentration of lactate ion. So both of these are 8.7 10 to the negative 3 molar. Therefore, the Ka for lactic acid is the concentration of H2O plus square divided by 0.1 minus the concentration of H2O plus. Therefore, the Ka is 8.7 10 to the negative 3 square divided by 0.1 minus 8.7 10 to the negative 3, and you will find a value for Ka of 8.3 10 to the negative 4. Calculating a nominal concentration or initial concentration. So question 10. What formic acid solution of Ka 2.1 10 to the negative 4 will yield a pH 2.42? So we have again the equilibrium that is being established. We can write our ice table. The nominal concentration is the initial concentration. That is what we are looking for. Initially, we have no H2O plus, no formate ion. There's a change. A little bit of formic acid is converted into H2O plus and formate ion. At equilibrium, we have a concentration of formic acid, which is the nominal concentration minus what has been deprotonated, and the concentration of H2O plus is plus X. Concentration of formate ion is plus X. So we have the expression of Ka for this equilibrium that is going to be X squared divided by C, the nominal concentration, minus X. If we rearrange this equation to solve for C, we can write that the concentration of acid, the nominal concentration, is X squared divided by Ka plus X. You need to recognize that in all of these questions, X is always the concentration of H3O plus. Look at it here. So we can calculate X as being the antilog of the pH, 10 to the negative 2.42, which is 3.8 10 to the negative 3 molar. It's also the concentration of the formate ion. So now, replacing this value into our expression for the nominal concentration, it's going to be 3.8 10 to the negative 3 squared divided by the value of our Ka, 2.1 10 to the negative 4, plus 3.8 10 to the negative 3, so plus hex here, the nominal concentration of our acid was 7.3 10 to the negative 2 molar. So we can say that a solution of formic acid of concentration 7.3 10 to the negative 2 molar has a pH of 2.42. Now calculating the pH of a weak acid solution. Question 11. Find the pH of a 0.1 molar solution of acetic acid, Ka 1.8 10 to the negative 5. So we have at equilibrium this equation that is being established. The concentration of acetic acid at equilibrium is the nominal concentration minus X. Concentration of H2O plus is X. Concentration of acetate ion is X. Again, we can write the expression for Ka. It's going to be concentration of H2O plus square, since these two are the same, over the nominal concentration minus the concentration of H2O plus, since X equals H2O plus. So we can again write our expression of Ka as being X squared divided by the nominal concentration minus X. What we want to solve for is X. X is the concentration of H2O plus. So if we rearrange this, we are going to have Ka times Cha minus X equals X squared, which gives us a quadratic equation, X squared plus Kax minus Cha times K equals 0. So we need to solve a quadratic equation. And you see this sad face here because we don't like solving quadratic equation. We need to know the solutions for quadratic equation. What if we could make our life easier? What if X was very small in front of the nominal concentration? What we're saying here is that this is a weak acid, and there's only very little H3O plus compared to what we put in of acetic acid. If we can say that X is very small in front of the nominal concentration, then we can neglect X in front of the nominal concentration. And we can say that Cha minus X is pretty much equal to the nominal concentration. In other words, there's only very little of our weak acid that has given H2O plus. If we can say that, then we can say that, well, Ka equals X squared over the nominal concentration. This one is gone. And we can solve for X as being the square root of the nominal concentration times Ka. That would be gorgeous, wouldn't it? But how can we tell if we can make this approximation? How can we tell if X is less than the nominal concentration? For this, we are going to look at the ratio of the nominal concentration over the Ka. If this ratio is greater or equal to 100, then X is very small in front of the nominal concentration. Our error will be less than 5%, and we'll be able to solve for X as being the square root of the nominal concentration times the Ka. If the nominal concentration divided by the Ka is less than 100, then really we must solve the quadratic equation. We won't be able to do the approximation, and we'll have to solve X squared plus Kax minus Cha times Ka equals 0. If we're not sure, we're going to do the approximation. We're going to say X equals the square root of the nominal concentrations times Ka. If what we find for X is smaller than 5% of the nominal concentration, then our approximation was allowed and we have the result. This is what we call the 5% rule. if x divided by the nominal concentration times 100 is less than 5%, our approximation is allowed. All right, question 11 followed now. Let's check our ratio CHA over Ka. It's 0.1 divided 1.8 10 to the negative 5. We get 5.5 10 to the positive 3, which is greater than 100. It means that our approximation is allowed. X is very small in front of the nominal concentration. So we can calculate X as being the square root of the nominal concentration times Ka. So X is the square root of 0.1 times 1.8 10 to the negative 5. It's 1.3 10 to the negative 3 molar. Let's check our 5% rule now. X over CHA times 100 should be less than 5%. If we replace the values here, we get 1.3 10 to the negative 3 divided by 0.1 times 100 is 1.3%, which is less than 5%. Our approximation was allowed. What does it mean though? Let's double check. Let's make sure really that X is negligible in front of the nominal concentration. If we look at CHA minus X, it's 0.1 minus 0.0013, our concentration of H2O plus, which gives us 0.0987. If we look at our sig figs, this is actually 0.10, the nominal concentration. So we can neglect X in front of the nominal concentration. The approximation was allowed. So then remember, we have solved for X, but what is X? X is actually the concentration of H3O plus at equilibrium, which is what we're after since we're after the pH. So pH is minus log of X. It's going to be 2.89. We have 2 decimal places because we have 2 sig figs. All right, question 12. Find the pH of a 0.1 molar solution of an acid HA of Ka 4.0 10 to the negative 3. We have our equilibrium that is being established. Let's find out if we can make the approximation. CHA over Ka is 0.1 divided by 4.0 10 to the negative 3. It's 25. It's less than 100. Which means that we cannot make the approximation. We have to solve the quadratic equation. Where does this quadratic equation come from? Remember, it comes from the expression of Ka. Ka is x squared divided by nominal concentration minus x. If we rearrange that, Ka times CHA minus x equals x squared. Further rearranging that, our quadratic equation is x squared plus Kax minus CHA times Ka equals 0. Solutions for quadratic equation of the form ax squared plus bx plus c equals 0 are x equals minus b plus or minus the square root of b squared minus 4ac divided by 2a. So here a equals 1, b equals Ka, and c equals minus CHA times Ka. So this minus 4ac here is going to become plus. If we plug in the numbers, we're going to have x is minus Ka plus or minus the square root of Ka squared plus 4 times CHA times Ka, the whole thing divided by 2. If you plug in the numbers and do this calculation here, you will find that x is minus 4 10 to the negative 3 plus or minus 4.02 10 to the negative 2 divided by 2. If you take the solution with a minus here, your nominator overall is going to be negative, which means that x is going to be negative. So it's not a valid solution. The only valid solution is the solution with plus. So if you do the calculation now, you will find that X equals 0.018 molar. From that, remember, this is the concentration in H3O plus. So we can find the pH. The pH is minus log of 0.018 molar. Our pH is 1.74. So let's check that indeed the ratio of H3O plus over the nominal concentration times 100% is greater than 5% in that solution. So remember, X is 0.018. The nominal concentration was 0.1 times 100, it gives us 18%. So the acid HA in this question 11 was 18% dissociated. That introduces the concept of person dissociation. The person dissociation tells you how much the equilibrium is towards the formation of H3O plus and A minus. Recognize that X is the concentration of H2O plus. So when we calculate this person dissociation by XA divided by CHA times 100, we are actually calculating concentration of H2O plus divided by the nominal concentration times 100. This corresponds to the dissociation of HA, how much HA has been dissociated into H plus and A minus, and H plus reacts with water, how much HA has been ionized into H3O plus and A minus, how much HA has been deprotonated, has lost its H plus. So we call that a person dissociation, a person ionization, or a person deprotonation. Given a person deprotonation, person dissociation, and person ionization for a solution, we can calculate, based on the nominal concentration, the concentration of H2O plus. This person dissociation, ionization, deprotonation depends on both the value for the equilibrium constant and the nominal concentration. Question 13. Calculate the person dissociation of solutions of acetic acid. Acetic acid has a Ka of 1.8 10 to the negative 5, and we have two cases. Case A, the nominal concentration is 0.1. Case B, the nominal concentration is 0.001 molar. So let's start with case A. Doing the ratio nominal concentration over Ka 0.1 divided by 1.8 10 to the negative 5, it's much greater than 100, so we can do the approximation. X is the square root of the nominal concentration times the Ka. If we do this calculation, you'll find that X is 1.3 10 to the negative 3 molar. In the case of a nominal concentration of 0.001 molar, the ratio nominal concentration over Ka is 0.001 molar divided by 1.8 10 to the negative 5. It's 55. We have to solve the quadratic equation. Remember, it's minus K plus or minus K squared plus 4CHA times Ka divided by 2. Only the plus will work. We'll find that X is 1.3 10 to the negative 4. Now, let's look at our person dissociation. The person dissociation is going to be X divided by the nominal concentration times 100. So for case A, we have 1.3 10 to the negative 3 divided by 0.1 times 100. And for case B, we have 1.3 10 to the negative 4 divided by 0.001 molar times 100. If we do this calculation, you see that when we have a 0.1 molar solution of acetic acid, the person dissociation is 1.3%, but when we have a 0.001 molar acetic acid, the percent dissociation is greater, is 13%. So for the same acid, if we have a lower concentration, we will have more dissociation. All right, let's do one last question. Cacodylic acid is used as a cotton defoliant. Cacodylic acid is 0.77% deprotonated in a 0.001 molar aqueous solution. What is the pH of the solution? And we have a number of choices. Remember the equilibrium that is being established. Cacodylic acid, you can symbolize it as HA, gives H3O plus A minus. And remember what the percent deprotonation is. It's H3O plus divided by the nominal concentration times 100. So if we rearrange this, the H3O plus concentration is the percent deprotonation divided by 100 times the nominal concentration. And the percent deprotonation is given here when we say is 0.77 deprotonated. It means that the percent deprotonation is 0.77%. So we can solve for the concentration of H3O plus. H3O plus excuse me, is 0.77 divided by 100 times 0.011 molar, which is 8.5 10 to the negative 5 molar. So our pH is going to be minus log of 8.5 10 to the negative 5. And we'll find that the pH is 4.07. 2 digits, because we have 2 sig figs. So here the answer is D. One more question. What is the Ka? And again, we have different values, different options. Remember, the expression of Ka is X squared, which is the concentration of H3O plus square, divided by the nominal concentration minus X, which is the concentration of H3O plus at equilibrium. We know the concentration of H2O plus at equilibrium. It's 8.5 10 to the negative 5. So we can replace the numbers in this expression of Ka, 8.5 10 to the negative 5 squared, divided by 0.011, which is our nominal concentration, minus 8.5 10 to the negative 5. The Ka for this cacodylic acid is 6.6 10 to the negative 7. All right, students, this concludes Module 18 and calculations with weak acid. On Module 19, we'll talk about bases. Bye!